So I would thank the organizers for inviting me. So let's first give you a few simple knowledge about transition metal dichalconides. So you have a metal layer here, and then on top and at the bottom of it you have the chalconides. For example, this is molybdenum or tungsten, and the crystal phase is this 1H phase, while if the metal is, let's say, titanium, vanadium, thallium, it's typically 1T phase. And the difference is simply, you look simply at just triangles here. They are rotate with respect to each other. So if we compare some of the structural dimensions, so this is the distance between the metal and the dichalconide, you see that in the selenium ones, it's a little bit larger. Also, the distance between the metals is a little bit larger. And we also heard already that if you decrease the number of monolayers, the band gap increases and you get this indirect to direct transition. So I will be talking about three different materials. On the one hand, molybdenum, the selenite, and I will tell you something about the effect of strain on such monolayers, that you can induce band gap transition from direct to indirect, and I will also look at the phonons. Then in tungsten diselenite, there the direct to indirect transition is much softer, and even for a number of layers you can still see the direct transition or contributions of the direct transitions, all through that the indirect band gap is the smallest one. And then there's something particular with the Raman spectrum, where theoretically you expect a single peak, while experimentally you see two peaks. And then a new member in the family is rhenium disulfide. And this is a material which is quite different from the other ones which we know up to now. For example, you do not have a direct to indirect transition there if you change the number of layers. And I will also say something about possible defects in this material. So the study of those three here was motivated by experiments. I'm doing theory. So our methodology is based on computational DFT calculations, where we typically use the VASP code and the quantum espresso. And the exchange correlation is, we typically use GGA and also van der Waals, and in these materials, spin-orbit interaction is also very important. If you are really concentrating on the band gap, then you have to go one step further and use this type of approximation. Our experimental colleagues, they used three different types of experiments. So optics, photoluminescence spectroscopy, for the phonons, Raman, and then structural AFM, or also transmission electron microscopy. So let's start with molybdenum diselenite. So in this paper, Nanoletters, they found that in the bulk you have an indirect band gap of 1.2 eV, and the monolayer has a direct band gap of 1.55 eV. And you see that clearly also in the PL spectrum, where for bulk you do not have any signal, while if you decrease the number of layers, you see this signal growing. Now, if you look at the electronic structure, and I will give you an example that you have to be very careful with calculations based on DFT. For example, when you use LDA, and what you find for the monolayer is that you have an indirect band gap, while experimentally you find a direct band gap. So you do a better approximation, you do GGA, and then you see this direct band gap appearing. So this here is a little bit larger. And then when you include spin-orbit interaction, you see this typical splitting of your conduction and your valence band, and also the band gap changes. So the splitting, spin orbit splitting in the conduction band is typically 24 millielectron volt, and in the valence band, of course, it's always much larger. It's an order of magnitude larger. Then, if you want to get the band gap correct, what we did is we did this G0, W0. You get a band gap of 2.33 eV. Then, in order to compare with the optical gap, you have to include the exciton energy. And that we estimated about 0.7 eV. So you get an optical gap of 1.6 eV, which compares rather well with what was found experimentally. Now, what's the effect of applying biaxial strain? So strain can be applied in different ways, as was already mentioned by the previous speaker. You simply put your sample on top of a flexible substrate and you simply band it. Or you can simply use an indentation technique, for example, an AFM. Or you can put your material on top of a nanostructured substrate. And in this way, you can also induce local strains. Now, how does the energy spectrum changes? So maybe I should stand on this side. So if we increase the strain, what you see is that if you have to look at these, the top of the valence band and the bottom of the conduction band, and you see that this one here is moving up, and that at a certain moment, for example here, this direct band gap and the indirect band gap are the same. And if you keep increasing the strain, then you see that you will have an indirect band gap. So what in essence is happening is that at the gamma point, the spectrum simply, the conduction and the valence band simply move up, and at the K point, it moves down, and at a certain moment, you have your crossing. So this is simply the energy band gap versus the strain. So this is the direct band gap at the K point, and that's this indirect band gap, that's the blue curve here, and you get a crossing about 2 or 3% of strain. If you include spin-orbit interaction, that moves a little bit to some higher strains, and if you do an even better calculation, so you see that around 3 to 4% of strain, you can induce simply a direct to indirect transition. So that means that by simply straining your system, you can change the optical properties in a fundamental way. Another thing is that if we look at the mass, so the mass of the electrons and of the holes are around 0.5. The holes are a little bit heavier, 0.6. So here we plot the normalized mass. That means the mass with respect to the value at 0 strain. And the electron mass, so that's given by the curvature here of the conduction band, does not change much. On the other hand, if you look at the whole mass, you see that at the K point, the whole mass is relatively small, and then if you go to the gamma point, the mass increases with a factor of 2 or 3. So that means if you are close to this indirect to direct transition, then you have, in fact, 2 pockets of holes with very different masses, okay? And they will contribute quite differently in the transport, and also the exciton properties, for example, will be also quite different. What about the lattice dynamics? So we are looking now at the phonons. So if we look at the bulk phonon spectrum, so you see that it's pretty different, quite different from what we are used to with graphene, because the acoustical and the optical branches are quite well separated. So these are the acoustical ones, the longitudinal and the transverse, and then you have this flexural phonon mode here, which has this typical K-square behavior. Now, the Raman active mode is those 3 one here. So these are the out of plane, and these are 2 are the in plane modes. Now, if you compare that with molybdenum disulfide, you see that the E2G mode has a lower frequency than the 8-1G. So this is this out of plane. And in molybdenum diselenide, they are completely reversed. Okay? That's one big difference. Another thing is that if you look at single layer and you compare it with few layer, this one here is quenched at the single layer level. So you have 3 Raman active modes, as I discussed already. This one is the most intensive one. Then you have the E2G. That's due to the coupling of the in-plane vibrations. And then this one, which I did not show here because it has a lower energy. Now, how do they change when I apply biaxial strain? So this is what happens experimentally. So you see that this mode here, the high frequency mode, in fact softens, so it redshift if you apply strain. And also the same with this one here. While this out of plane mode here, the one which has the highest intensity, seems to be pinned at around 230 centimeter minus 1. Now, and this also agrees with what we found experimentally, theoretically. So this here is the phonon spectrum. If you apply strain, you see indeed that this mode here goes down, and also this one goes down, while the A mode here gets stuck at the same frequency. So that seems to agree with experiment. The next material we looked at was tungsten diselenide. And I also will discuss here the electronic properties and the anomalous Raman spectra which we found. So this tungsten diselenide, so this is an AFM picture when you put it on top of silicon dioxide, where you have regions with single layer, bilayer, trilayer, and the steps are about 0.7 nanometer between the different layers. So what you find is, if you look at the PL signal, that if you go from single layer, so you have a very strong peak, so that it clearly indicates that you have a direct band gap, and then you put the second layer, you see it moves to lower energies, what's typically always found, and then the tri-layer. But even if you go to 7 and 11 layers, you still see 2 peaks here. So if we convolute these peaks, you find the direct band gap contribution goes like this here. So it, when you go from 1 to 2 layers, it suddenly decreases and then more or less stays the same, while the indirect band gap moves to lower energies. So let's try to understand this. So if we look for monolayer tungsten diselenide, and you see clearly that you have here a direct band gap. Also here, if you do LDA, you will also find that this bottom here is lower than the bottom of the conduction band at the K band, and you would also predict indirect band gap, while if you do the theory better, you find really the direct band gap. So you see that in this type of materials, the type of approximation you use can sensitively change the type of band gap. So, for example, GGA predicts a direct band gap, LDA indirect. The value of the band gaps are quite different. The top of the valence band is at the K point, while at the conduction band, it's not at the gamma point, but it's in between the K and the gamma point. And notice that the experimental value is 1.64 eV, which is closer to the LDA value, while a better theory gives you a value which is different from experiment. Okay? If you include spin-orbit interaction, so the reason is that you have to include spin-orbit interaction and also excitonic effects, then you find that the conduction and the valence band here, they split. Okay? Also, the valence band at the gamma point decreases in energy. You go from this red to this blue curve here. So the degeneracy of the conduction and valence band is lifted. And also the band gap here is 1.25, so it even decreases, and the indirect band gap is 1.3. So it means that those values are pretty close to each other, and that at optical transitions you can have various possible transitions at the same time. If you go to the bulk, you see that once you go from single to bilayer, the spectrum does not change much. The bulk is this dotted curve here. And now this energy, this indirect band gap, is smaller than the direct band gap. So if we look at the smallest gaps here, single layer is the direct, KK, while from bilayer to bulk, it's this one. But you see also that this indirect band gap value is very close. Furthermore, at the conduction band, you have this spin orbit splitting, which is tiny. It's only 40 millielectron volts, so which is of the order of the thermal energy, and that you have an almost triple degeneracy. So if you look at multi-layers, so you have both contributions from the direct band gap, while you would expect only contributions from the indirect band gap. Another thing is, if you look at the intensity of the one layer versus the two layer, it's only a factor between 1 and 10, while if you look at molybdenum disulfide, it's between 100 and 1,000. Okay? So there, you go immediately, in molybdenum disulfide, you go immediately from a direct to an indirect band gap, while for tungsten selenide, life is softer, and it goes much more gradual. Now, what about the phonons? So experimentally, if you look at the Raman signal, you only find one peak here. And that's, in fact, this peak here. So this is the theoretical photon spectrum. So you have those three modes here. So I'm only looking in this region. So you have the E2G and the A1G. But you see that they are degenerate. And that's why in bulk you only have one mode. If we go to bilayer, theoretically, you do not see any lifting of the degeneracy, while if you look at experimentally, you see a second peak appearing. Okay? So which does not agree with the theoretical results. If you then go to the single layer, this peak here starts to move to higher shifts, and it also becomes more pronounced, while the calculation still gives almost no lifting of the degeneracy. So what's the reason of this discrepancy, or what's going on here? So this is now, when I put all three results on top of each other, you see a small shift in the main peak, and then the appearance of this extra peak here. Now, at this point here, and that's the region we are looking at here, so that's around 250 centimeter minus 1, the contributions, or the phonons which are present there, you have the two E phonons. So that's this type of movement of the different atoms. This one, the red ones, are the ones which are Raman active, and this one here is also Raman active. This is the out of plane modes. So they have all the same energy up to 1 centimeter minus 1. And that's very different from what we're used to if we look at the other molybdenum and tungsten dichalconides. There you see clearly that these optical modes here, they are split in energy. Also here, you see, and also the tungsten disulfide. So you have clearly split energy between the A and the E, and that means that you would have two peaks, or at least three peaks, in your Raman spectrum. So in that respect, tungsten diselenide is really different and unique. So from where can this splitting of the Raman active modes come from, experimentally? So the thickness of each tungsten diselenide layer is about 3.5 angstrom, and that means that we have atomically thin layers. They are put on a silicon oxide substrate, where the substrate has a certain roughness on the same length scale or as the thickness of your layers. So that means that the substrate will induce some strain in your monolayer. And if you look at the substrate, it's an amorphous silicon dioxide, and you have like wedge-shaped hills. And if you put your tungsten diselenide on top of it, that will induce certain types of strain. So let's see what's the effect of this strain on such samples. So if we look at biaxial strain, so the arrows give you the direction in which the system is strained, compressed, and here dilated. So you see that these modes here, they are still state degenerate. They only shifted in energy. So biaxial strain cannot explain why the where you get a second Raman peak. Then if we use uniaxial strain, so that's in this way, or in the armchair in the zigzag direction, you see that indeed in that case the phonon energies, the degeneracy is clearly lifted, and you only need about 1% of strain here. So you have lifting of degeneracy, and in this frequency range, the lattice symmetry is broken, and most of the modes lose their Raman activity, and you get a shift which agrees more or less, or is of the same order of magnitude of what was found experimentally. So when you have this degeneracy, then this type of strain is going to be important. If you already have splitting, then this small extra shifts will not matter so much. So in my last part of the talk, I will talk about a new system, which is rhenium disulfide. If you look at the table of Mendeleev, this is where rhenium is, so it has about 7 electrons in the outer shell. Here's tungsten, molybdenum. These are the outer electrons, and the origin of this name, rhenium, comes from Rhenus, the Greek Rhenus, which means the river Rhine. And it was first, the name was given by those Germans here in 1925. They already, in the beginning of the 1900s, there were already some reports by a Japanese who seems to have discovered this material, but they were the first who really identified it. So the rhenium has many different oxidation states. Okay? Then the rhenium disulfide, it's a mineral, rhenite, and it's a mineral which is very rare and which was not long ago discovered in Russia in some volcanic island. So what's the lattice structure? So we know that the molybdenes and the tungsten dichalconides usually have the 1H phase. So if we tried to look for rhenium disulfide in this phase, what we see is that the phonon spectrum here has imaginary components. So if I plot the phonon frequency as being negative, it simply means that the phonon frequency is imaginary. So that means it's not stable. Okay? The 1T phase, it's the same. It's also not stable. If we now take the 1T phase and let the system relax, we find distorted 1T phase with real phonon frequencies. I will discuss a little bit later how this distortion really happens. You see really change formation here. Now the lattice parameters here, they are a little bit in between those two here. Now if we go from the 1H phase, so when we force the system in the 1H phase, as long as you do not look at the phonons, you can calculate the electronic energy, and you compare it with the energy of the 1T phase. The 1T phase has 0.9 EV lower energy. If the 1T and the distorted 1T phase is 1.1 EV.
Per atom.
Sorry?
This is energy per atom.
Per unit cell.
Per unit cell.
Yeah. So the crystal structure looks as follows. So you have a chain formation, so a chain reconstruction. So that's like a Peierls distortion, which breaks the hexagonal symmetry. And now the unit cell looks like this. So that means that the unit cell is now twice larger. So it contains 4 rhenium atoms, that are these, and then those sulfur atoms here, 8 sulfur atoms. Furthermore, the system is anisotropic if you go along the A or along the B axis. Another interesting thing is, if we, at the rhenium atoms, they are really sitting in a layer, but the 4 sulfur atoms, they have different distances with respect to this layer. So it looks like those silver atoms form 4 different layers of silver atoms. So it means that rhenium disulfide is like a 9-layered system, while molybdenum disulfide, it's a 3-layered system. Okay. Now, if you look here at this, those change here, what happens is that you get extra bonds between the rhenium atoms here. And this is understood as follows. This here is the charge density plot of the bonding level. So here are the rhenium atoms, and you see clearly here those bonds appearing. And this is for the undebonding states. Now, rhenium has 7 electrons, and 6 of them, they participate in a covalent bond with the sulfur. So that means if you force the system in a 1T or a 1H structure, you have this one dangling bond there. And that means that that's energetically unfavorable. So what happens is that this dangling bond turns to the other rhenium atom, and they form a covalent bond with each other, and that results to the rhenium-rhenium chains. Now, if you look at the interlayer interaction, so we take 2 of those layers, then if we look at the interlayer binding energy in millielectron volt, and this is also per unit cell, then, and we did the calculation for different exchange correlation functions, you see that in the rhenium diselenate, this is much smaller, at least a factor of 2 to 3 smaller than as compared with molybdenum disulfide. So those atoms are extremely weakly van der Waals bound. You can also see that if you take 2 of those layers and you slide them with respect to each other, and you calculate how the energy differs. So if you slide in this direction, that's along the A-axis, the B-axis, or diagonal here, the variation in the energy is only on the level of a few millielectron volt. And it's very different with molybdenum disulfide, where this variation is about 200 millielectron volt. If you move it in the A or the B direction, of course it's the same because they are equivalent, and along the diagonal, that's like this here. So that's another indication that the interlayer interaction is really weak here. And that also means that if you stack them on top of each other, you will find many different possible stackings. Okay? Now, what's the reason of that, of this weak interlayer binding energy? We know that in those transition metal dichalconides, you have your metal atoms, and then you have your sulfur or your chalconite atoms. The metal atoms are typically positively charged. And you have an energy charge transfer from, for example, in this case, the sulfur and the rhenium atoms. So they are typically negatively charged. So the charge transfer in the case of rhenium disulfide is only 0.4 electrons per unit cell. While in the case of molybdenum disulfide, it's between 4 to 5 times larger. So that means that the polarization in that case is much larger. And we know the van der Waals interaction is a result of fluctuations, charge fluctuations. So it's direct related to the possibility that you can polarize the system. So that means that rhenium disulfide has a much smaller interlayer polarization than molybdenum disulfide, but of course a larger intralayer polarization. Now, if we calculate the total energy as function of the interlayer distance, also here you see a dramatic difference. In the case of molybdenum disulfide, this here is the equilibrium interlayer distance, and that means to separate 2 layers you need 460 millielectron volt, half an electron volt per unit cell to separate the layers. In the case of rhenium disulfide, it's 6 times, it's only 8% of the value of molybdenum disulfide, so it's 18 millielectron volt per unit cell, so they're extremely weakly coupled. Now, what about experiments? Okay, so this is an AFM picture of such a monolayer exfoliated on silicon dioxide that was CVD grown. Then If you look at the structural characterization, so this is high-resolution transmission electron microscopy images, then what you find is that they have a very good crystalline quality. If you look at the unit cell, it agrees with trigonal distorted MOS2 structure, and that there's also a lack of some specific type of stacking. So you can, it's a little bit like randomly stacked. And also the interlayer spacing varies a lot. You see 0.9 angstrom, while in molybdenum diselenite, this interlayer spacing, it only varies 2% of an angstrom. So the electronic band structure, here I compare the bulk result, which is the green curve, and the dashed curve is the monolayer. And you see that in both cases, the spectrum looks very similar. The band gap only increases with about 80 milli-electron volt. Another thing is that both the single layer and the bulk have a direct band gap, and at the gamma point, not at the K point. Okay?
So is this in that distorted structure that you showed?
Yes, yes.
Would be the equilibrium one?
Yeah.
Okay.
So from now on, I only talk about the equilibrium configuration. Okay? So it's a direct band gap semiconductor with a band gap which almost does not depend on the number of layers, and the band gap is at the gamma point. So that's really different from the other transition metal dichalconides. If we look at the density of states here, the energy scales is a little bit different from here. You see that both at the conduction band and the valence band, at the top of the valence band and the bottom of the conduction band, both rhenium d electrons and the p sulfur atoms contribute to the density of states. Okay? And the majority is still this rhenium d states. Now, if you do PL, what you see is that the PL signal does not really move with the number of layers, except for the monolayer, there's a small movement. If we look at the PL intensity, and this is the renormalized one, so with respect to the number of layers. So for rhenium disulfide, it's almost constant. Okay? So it's almost proportional to the number of layers. While in the other, the molybdenum and the tungsten systems, you get a very fast decrease of this PL intensity, and that's due to the fact that you go from a direct to an indirect band gap. If you look at the peak position, so the rhenium disulfide, you see it's almost flat and only from monolayer to bilayer. So bilayer is already bulk. Okay? While the other system, you see, they vary a lot with the number of layers. So that agrees also qualitatively what I showed you, the density functional calculations. Now, of course, if you have very weakly bonded layers, then the one thing to do is simply apply pressure and see what happens. So you see that if you look at the absorption, it almost does not change if you apply even pressures up to 7 gigapascal. The band gap, we already also does not change much, and the photon modulated refractive reflectance also not. So if the out-of-plane elastic modulus is only 0.4 gigapascal, while in molybdenum disulfide, it's 50 times bigger. Okay? And that means that if you apply a pressure of 7 gigapascal, you will change the interlayer distance a lot in the case of rhenium disulfide. And still it has a very little effect. Also, if you look at the change of the gap in molybdenum disulfide, it changes with about 0.02 EV per gigapascal. That means that if you would apply a pressure of 7 gigapascal, the band gap would change with 0.14 EV. Here it changes at most with 0.04 EV. Okay? So the overlap, so the conclusion is the overlap of the electron wave functions from adjacent layers is much weaker in this material than in this molybdenum disulfide. And that the modulation of the interlayer distance cannot renormalize the band structure in this material. So the last part is on the almost last part is on the lattice dynamics. So this is for single layer rhenium disulfide. Okay? And this here is the bulk. Okay? Here I only show the result for gamma to M, so this region here. And also here you do not see big differences. Okay? In the case of a single layer, you have 36 non-degenerate eigenmodes. Okay? While in the case, of course, if you have a bulk, it's doubled. And these phonons are rather different from molybdenum disulfide, where you clearly see separate acoustic and optical modes, while here they simply move through each other. So that means also that most eigenmodes which you have are mixed in-plane and out-of-plane motions of the rhenium and the sulfur atoms. And of course that will have an influence on the Raman spectrum. So this here is the experimental result for the Raman spectrum. And that's now the calculated phonon spectrum in the window of 100 to 400 centimeter minus 1. So we have about 29 phonon branches, and in the Raman spectrum you find about 11 peaks or Raman active modes. And the dominant one is this one here. So that's the A1G out of plane motion, but you also see that you also have a coupling in of in-plane motion, and the same with the E2G here. And these are some other modes here. Okay. So if you look at the errors, it's not all pure in-plane or out of plane. Now, if you look at the Raman signal for bulk and monolayer, there's almost no difference. Okay? So also on the level of the lattice dynamics, the different layers are not coupled. So while if you look at the molybdenum disulfide, you see that if you go from bulk to monolayer, you find that the E2G stiffens about with 5 centimeter minus 1, and the A, so the out of plane motion, softens with almost the same value. While here you see no changes, and you have some extra peaks which are also a result from the coupling with the phonons, which are a consequence of the low crystal symmetry. The effect of pressure on the phonon modes. So this is the hydrostatic pressure. So if you look at the AG mode here, molybdenum disulfide, so that has the highest frequency, while here it has the lower frequency than the EG mode. So you see this one here changes much more than the rhenium disulfide. Okay? And so the change here is only a few centimeter minus 1. So this one is in fact not a pure AG mode, so out of plane mode, because you also have some in-plane mixing, and those they are more sensitive to pressure. Now, if we take into account that the ratio of the elastic moduli of molybdenum disulfide and rhenium disulfide is about 50, then you will find that the deformation coefficient of the out-of-plane vibrations is expected to be a few orders of magnitude smaller than in the case of molybdenum disulfide. And the last part, what about defects in this system? If you, of course, you have now 4 different sulfur atoms, and it turns out that this sulfur atom here, which sits between the rhenium chains, and these are the rhenium chains, that if you make their vacancy, that has the lowest formation energy. And the effect of the density of state is the following. So if you put here vacancy, the band cap decreases. Okay? And what's happening is that you get extra density of states at the top of the valence band. So that it means that such a sulfur vacancy acts like a donor. Also, when you put more sulfur vacancies, they do not stick together. Like, for example, in graphene, you tend to form complexes. Here, they repel each other. The rhenium vacancy, also here you have different, 4 different rhenium atoms in a unit cell. This one has the lowest formation energy. And different from the sulfur vacancy is here that this one will be spin polarized. So this is spin up and the bottom is spin down. Now the band gap decreases from 0.43 eV to 0.35 eV. In fact, what's happening is that you create mid-gap states here, okay? And you get a spin polarized state, and the spin polarization per rhenium atom is about 1 Bohr magnetron. But the formation energy here is much larger than in the case of the sulfur vacancy. It's about a factor of 2 larger. Now, where is the magnetism located? So you see this here is the rhenium vacancy, and you see this is spin up and the red is spin down, that most of the spins, polarized states, are connected with the sulfur p atoms. Now, if you compare the energy difference between a spin unpolarized and a spin polarized state for rhenium disulfide and molybdenum sulfide, it's about 10 times larger in rhenium disulfide. Okay? So magnetism is expected to be more robust. And you also find that the formation energy for a sulfur vacancy in rhenium disulfide is smaller than the one in molybdenum disulfide. So it means that it will be more prone to point defects in that case. So the summary. I studied the effect of strain on monolayer molybdenum diselenide, where you get a direct to indirect band gap transition when you apply about 3 to 4% of biaxial strain. If you go even to higher strain, you get a semi-metal. And near the transition, you get a coexistence of different Hall states with very different masses. And we also found that the Raman peaks shift, but the dominant one, so this out of plane, that does not change much with strain. In the tungsten diselenide, the electronic properties are rather different. You get a more softer indirect to direct band gap transition. And what makes this material so special is that you get this accidental degeneracy between the A and the E Raman modes. And that the experimental observed appearance of an extra Raman mode, we think it's a consequence of strain induced by the substrate. Then rhenium disulfide is very different properties, which is almost independent of the number of layers. So you can do monolayer physics with multi-layer structures in this case. And the system is also more prone to defects than molybdenum disulfide. So let me thank my collaborators. There's a theory part and experimental part. Theory, these are my postdocs in Belgium who collaborated on this. They're all from Turkey, as you can see on the names. And we also had a collaboration with people from Spain, from the Basque country. And the experiments were done in Berkeley, and there was also collaboration with people from China and Taipei. So thank you very much.